Good morning, everybody. First of all, I'd like to thank NAMIC for giving us this opportunity to speak here. My subject matter today will be DMD, right, or rather direct matter deposition, right. Now, in the AM world, a lot have been said about powder bed fusion, but very little is known about DMD or DED in short. Some even argue that DMD is not AM, which I don't quite agree. So in the next half an hour, I will attempt to refute this argument and show why DMD is in fact part of AM. Right, but before I begin, like all good show, there must be some advertisement to complement it. So without further ado, I'd like the audience to allow me to introduce what voestalpine is all about. All right, briefly, voestalpine is in the steel business. To be exact, exotic steels in the form of plates, bars, and whatnot. We employ about 52,000 employees worldwide in 500 companies within 50 countries, and we have a turnover of approximately 13 billion euro last year. voestalpine is further divided into 4 divisions, and the division that I'm working in now is known as the High Performance Metal Division, right? Now, where does all the AM activities reside in this division? All right, it is actually in this organization which we call VAMC, which is voestalpine Additive Manufacturing Center. Right, so worldwide we have 7 locations that are actively pursuing AM activities. Right, these are known as AM Center of Excellence. We have 2 powder manufacturing center, with the rest of the centers being printing or service bureau. And the focus in Singapore is purely on DMD, right? Okay, powder atomization. Production have started since 2016, and we are able to produce about 80 tons a year. Melting is conducted through vacuum induction and atomization with inert gas. Okay, 4 standard product lines, and with 3 more coming in the pipeline. Particle size ranges from 15 microns to 150 microns, and minimum order quantity comes in 10 kilos or multiples of 10 kilos. Right. If you buy from us, you will see a standard packaging in this form. Okay, the machines that we operate within the various printing center ranges from EOS, TruePrint, SLM, Renishaw, Beam, Lasertec, and True Lasers, right? Now the Singapore bit, like what I've highlighted earlier, our focus is only on DMD. Right, this center is operational since 2016, located within the metal business. The technology that we focus on is DED, right? And we have a production area of about 8,000 square feet with a lab space of about 2,000 square feet. Full-time employees, we have 8 people running around manning the shop. Okay, the machines that we operate within the facility are the DMG Mori, which is equipped with a 5-axis CNC workstation, and the Beam 400, which comes with a controlled atmospheric chamber. Now, why DMD? We feel that we like the part size, right, and the deposition rate as compared to powder bed fusion. And this technology actually suits our needs and focus within our playground, right? Okay, we have developed to date 12 powders fully qualified with our machines. Next in line, we will be playing with tungsten carbide and other tailored compositions. Okay, before jumping into bed with printing, there are a few things that we all need to abide to. Now, whatever applies to powder bed applies to the DMD technology, right? So you still have to know your powder. You will still need to understand your process parameters, and of course, last but not least, your process controls. Now, are all powders equal? Are they the same, right? So in DMD, like what I've said earlier, powders being powders, powders are not the same, right? You still have what we call the good powder and the bad powder. And to understand your powder, you still need to understand things like the morphology, the PSDs, humidity, oxygen content, chemistry, and the flowability. As for process parameters, you will need to understand your parameters and your overlaps, right? Last but not least, process control. You will need to understand with every powder, where is the sweet spot? How do you control your prints, right? How do you control your lasers, right? Last but not least, after mastering the 3 Ps, you will need to find out or check the integrity of your prints, and this will be done traditionally with mechanical tests to suss out the properties and the prints that you are making, right? Now, what are the attributes in DMD? Right, in print mode, what we have observed so far and getting repeated results is that there's very low porosity observed in almost all the prints that we have made. The grain structures are almost very uniform and fine as compared to raw material. Okay. Now in hard facing mode, what surprises us most, and again, very consistently, what we have found is that the heat affected zone, right, it's very narrow, right, and the grain structures are in really good shape, fine, consistent, and uniform. A comparison between HVOF and cold spray, we found that DMD actually provides a better metallurgical bond with tiny porosity, and it allows us to build up to 5 mm in thickness, right, without much problem. Right? Again, on grain structure, if we compare it against gas tungsten arc welding and plasma transfer, we consistently found that high hardness is achieved with very low dilution, right, and with minimal heat input, right? Now, this leads to a case where we see DMD being a good alternative for applications such as hard facing, right? As seen in these two examples, right? It creates very narrow heat affected zone, good bonding, and high hardness is achieved. So DMD in our findings are actually very good alternatives for both well cladding and HVOF process. Okay. Moving on, if you look at the microstructure at the interface of the heat affected zone and hard facing area, you'll observe what I've been repeatedly saying about the heat affected zone and the microstructure, right? Fine grains, narrow heat affected zone, right? And if you look at it carefully under the microscope, you will find that it is free of cracks and a circular grain boundary precipitations. Now, overcoming complexities, how do we deploy this technology? What we think DMD is good for, we could look at new builds, although it is not as strong as opponent as what we see in powder bed, but it certainly can be deployed. We also see good application in repairs, and last but not least, the strongest point about DMD is actually in hard facing, right? Okay, this is a case where a polygonal structure is called for, and the challenge is to get the thickness down to 1 mm. This is a new build that we have achieved with our DMD technology, right? And if you look at what DMD or so-called AM could do to a traditional part like this, it actually reduces 4 operations into 1, right? Without any further post-processing. Next case, again, it's a case where the supplier is probably long gone. Either the supplier is dead or the shop has closed shop, right? And we did this elbow print with our machines, right? No MOQs required, very little material removal, and there's a wide selection of materials. We actually print this elbow with the material called Corex. Okay, in repairs, what we have done on this impeller. This impeller was brought to us in the form of the colored picture with 1 blade gone, right? What we have done is we have repaired the blade, we have put in a new blade, and we have also coated the pitted blades with hard-facing material and put it back in action, right? So this is what we can do with DMD in the repair arena. Of course, I've been talking a lot about hard-facing, which I think this is the strongest point in this technology. We have done a lot of studies, and we have done a lot of work in this area. Some of this work that we are doing is actually in validation phase for the oil and gas industry, right? Like I said, the heat affected zone, the narrow heat affected zone is giving the DMD process a very good advantage to replace some of these works that are traditionally done through cladding, right, in the welding process. So in comparison, what we have found, as compared to traditional manufacturing method, DMD or AM does not require MOQs, definitely no more required, reduction in prototyping time, very minimal post-weld heat treatment, especially with DMD process. There's also a higher process stability that is achieved with DMD, less failure and porosity as compared to castings. As compared to powder bed fusion, it has got a faster deposition rate, less stringent powder requirements, and minimal or no post-weld heat treatment from the parts that we have built so far, right? Okay, the last topic that I have will be the impact of AM in the oil and gas market. You heard from the last speaker that AM is not moving as fast as we have hoped for. That's true, but it's beginning to warm up, and we have seen a lot of inquiries and a lot of activities happening, especially in the North America, right? So common trend where customer comes to us for AM builds will be combining multiple parts into one, cost reduction through a hybrid build, right? Exotic materials, right, that usually require MOQs, right? If you go the printing way, there's no MOQs required, right? The fourth point, replacing mold or casted parts with AM parts, right? If you have a new article number and needs to be mass produced, you usually require casting, you usually require a mold. And if you go into AM, this is not required at all, right? Last but not least, designing intricate flow cavities that wasn't possible in the past, right? We are seeing a lot of this kind of work happening. And the early adopters in the oil and gas industry, what we have seen mainly in the wellhead and downhole activities. Right? Right, thank you.